This lesson we're going to begin a new topic called conic sections. Now, conic sections are based off of intersecting two cones where their points of the cones touch. So a picture like this. When we look at these cones that are inverted on top of one another and we intersect them with a plane, we get a couple of different cross sections, which gives us the four primary conic sections. The four primary conic sections are circles, ellipse, parabolas, and hyperbolas. So let's look at the first two, circles and ellipse, because these two are really related to one another. If I took this inverted cone picture and I intersect it with a plane, that plane would just cut through one of the cones, and if that plane cuts completely through one of the cones, not including the base of the cone, I would get two pictures, this one and this one. If my plane is perpendicular to the cones, so my plane is going this way, my cones are going this way, I would get the intersection to be a circle. If my plane is slanted slightly, so not perpendicular, but still only cuts through one of the cones and not the base, I'm going to get this oblong circle, or an oval, which we also call an ellipse. It's not going to be perfectly round all the way around, have the same radius all the way around. So the two intersections that I can create by looking at these double cones and intersecting with a plane are a circle and ellipse. These are my two conic sections. Now there's other things I can get. I can take that plane, only cut one of the cones, but also cut through the base of one of these cones. And this would be this picture. Well, if this plane slices through the cone, but also cuts through the base, I'm not going to get a completely enclosed curve. What I'm going to get is just this curve that looks like this. What that gives me is a parabola. And then the fourth possibility is if I take a plane and cut both cones. So here's a plane, that plane is going to cut through both cones. The intersection, if it goes through two of the bases, is going to be like a parabola here and a parabola here, similar to the previous picture. These sort of catty-corner parabolas create what we call a hyperbola. So there's four main conic sections. Now there's also a couple of other conic sections that we call degenerate conic sections. Let's say, I'll just look at one or two of them. Let's say we took this cone and my plane was perpendicular to the cone but cut straight through the point. Well, if this is my plane and it cuts straight through that point, the only intersection between the two of those things, the cones and the plane, the cross section would be just a point. So a degenerate conic section could be a point. Also, let's say I take a plane and that plane's on such an angle that it's exactly the angle that runs along the edge of these cones. So that's my plane there. Well, if this is my plane, the intersection between the plane and the cones would just be this line that runs along this edge here. In that case, that line could be another degenerate conic section. We're not really going to talk about the degenerates much more than this, but just know that there are a couple of different types of conic sections you can get, other than circles, ellipse, parabolas, and hyperbolas. But the four main ones that we talk about are these. So each lesson we're going to sort of discuss more of these. The first one we're going to discuss is the parabolas. In order to discuss these different conic sections, one major piece to all this that's going to be part of every one of the definitions for the conic sections is distance. So you need to be able to find the distance between 2 points, and this should be an old formula. Everyone should be familiar with how to find the distance between 2 points, but just to review it, because it is a major part of this, we'll look at it. So if you look at the distance involved between 2 points, if you're given 2 points, one point is x1, y1, and the other point is x2, y2. If you want to calculate the distance between them, you subtract the x's and square it, subtract the y's and square it, and then add those together, square root, you get your distance. This is based off of the Pythagorean theorem and looking at right triangles. It really doesn't matter where it comes from right now. I mean, you should know, but let's just calculate distance. So I want to calculate the distance between these 2 points. So we'll call this one 0.1, this one 0.2. Doesn't matter which one's 0.1 and 0.2, the distance should be the same. So if I want to calculate the distance, I'll take the square root of the difference between the x's. So that's going to be -2 minus 3 squared, plus the difference between the y's. So that's going to be 5 minus 4 squared. So I get the square root of -5 squared plus 1 squared, or the square root of 25 plus 1, which is the square root of 26. So the distance between these 2 points is the square root of 26. If I could simplify that square root using algebra, I would, but that's it. And it's a fairly easy thing to do. I think everyone should be familiar with calculating distance between 2 points. Again, that's going to be part of all our definitions. So let's look at the definition of a parabola. Everybody should be familiar with what a parabola is and what it looks like. But what we need to do is sort of look at this definition in a little bit more detail, and that's what's going to happen here. I think most people know what a circle, what an ellipse, what a parabola, hyperbola are, but we're going to look at them in a little bit more detail in sort of ways maybe you're not familiar with. So here's our definition of a parabola. A parabola is the set of all points pxy in the plane whose distance to a fixed point, called the focus, equals the distance to a fixed line, called the directrix. This definition you could probably read about 5 times. It might not make a whole lot of sense until we start to look at this picture here. When I look at this picture here, this red is my parabola, right? Everybody knows what the shape of a parabola is, at least you should. So what it says is every point that makes up this parabola, here's a point here, here's a point here, there's a point here. I mean, there's infinitely many points. Every point here is going to be a fixed distance between a point and a line, meaning it's going to be an equal distance between these two things. So here's our point, right? This point right here we're going to call our focus. This line right here is called the directrix. So if I look at this point here, the distance this point is to this point right here, this distance should be equal to the distance this point is to this line, which is this distance. So these two distances should be the same. I go to any other point on the parabola, this point, the distance this point is to the focus, which is this distance. The distance this point is to this line, which is this distance. Those should be equal. Now these two don't have to equal these two, but the idea is that these should be equal, these should be equal. And any point I pick that's on this parabola, whether it's this point, this point, this point, there's infinitely many points here that make up my parabola. All of them should have that property, that whatever distance they are to the focus should be the same as the distance they are to the directrix. Even this point right here, which you should know as the vertex point, the distance here should be equal to the distance here. This is the distance to the focus, this is the distance to the directrix. Alright, now we're going to label some of these things. Let me erase some of this. So if I look at my vertex as, say, a point on the parabola, and I call this distance here A, then this distance here also should be A. Now let's just say I made the vertex at point 0, 0. So that means the x-axis is right here, and this axis of symmetry to the parabola is the y-axis. Well, what would happen is that if this is 0, 0 right here, and this distance is a, the focus should be 0, comma a, should be the coordinates for the focus. And if this is a, and this point is 0, 0, then this on the y-axis should be at negative a, which would make the equation of this line, this directrix, to be y equals negative a. What's going to happen is we're going to look at parabolas in all different locations on the xy plane, but to start, we look at the parabolas where their vertex is at 0, 0. And once we look at the parabola where its vertex is at 0, 0 and understand how those parabolas work, we can more easily talk about how we can then move this parabola. So right now, if I label these distances a, I could come up with the coordinates for the focus and the equation for the directrix based off of knowing the distance here being a and the vertex being 0, 0. So you should be familiar with the equation of a parabola, understanding that it's a y squared or an x squared variable, the other variable being first power. So you're probably used to seeing, say, y equals x squared, and knowing this to be a parabola. Well, essentially that's the case here, but we're going to look at two different versions of a parabola. One where it's y equals x squared, and the other one where it's x equals y squared. Depending on which variable is squared is going to change your parabola. So we just looked at a picture where the parabola was shaped like this. The parabola shaped like this being the 0, 0 point, I have this focus point here, I have this directrix line here. If I know that this distance is a, I can come up with these equations. You could also look at a parabola where this is your y-axis, this is your x-axis, that looks like this. Still the vertex is 0, 0, but now my focus is going to be here and my directrix is going to be here. This distance is still going to be a, but that's going to change the coordinates of the focus and directions because everything's sort of turned sideways. The difference is here my y is being squared, here my x is being squared. So we have some equations of a parabola where the vertex is 0, 0. There are two equations. One which is y squared equals 4ax, the other one is x squared equals 4ay. Now with these equations here, these are the general forms for the equation of a parabola. The y is squared in the first one, which gives me this picture. The x is squared in the second one, which gives me this picture. The vertex in both of them should be at 0, 0. Now if I want to calculate the focus and the directrix, it's all about knowing this distance here. And that distance can be found by looking at the equation. In this case, the coefficient in front of the x to the first or the y to the first, we're going to call 4a. So if I want to figure out what a is, I take that coefficient in front of the x or in front of the y, and I divide that coefficient by 4, and I can figure out what a is. Once I get a, then I can figure out what the equations and the points are for my focus and my directrix. Now these functions are symmetric with respect to either the x-axis or the y-axis. If it's vertical, it's y-axis symmetry. If it's horizontal, it's got x-axis symmetry. I would call this a vertical parabola. I'd call this a horizontal parabola. So if I give you a question like this that said locate the focus and the directrix and then sketch the graph of this particular equation, first thing you're going to have to be able to do is recognize that it is a parabola. So how would you recognize it's a parabola? Well, it's got the form of y squared equals 24x or y squared equals 4ax. Only one of the variables is squared. In this case, the y is squared. So really what we have is this parabola. So the vertex, the focus, the directrix can all be found. But we really need to figure out what a is. Well, this coefficient in front of the x to the first power is 4a. So if 4a equals 24, then we have that a equals 6. Once you know what a equals, we could say that the vertex is 0, 0 because it's in this form. Any parabola in this form or this form has a vertex at 0, 0. Eventually we'll look at parabolas where the vertex isn't 0, 0 and the form of the equation will change, and we'll see that. But right now everything's going to stay 0, 0. Then what we know is that the focus, since it's in this form, should be 6, 0, the directrix should be x equals -6. And I don't have to put parentheses around that. I guess that's unnecessary. And the question said, sketch the graph. Well, sketching the graph's not hard to do. If I look at this, here's my y-axis, here's my x-axis. The vertex is at 0, 0. Since the y is squared, it's going to be a parabola that looks this way. The focus is going to be here, and that's going to be 6, 0. The directrix is going to be this line right here at -6. So that's going to be the directrix, and the idea is that every point, and my graph's not the greatest picture, but any point on this parabola should be the same distance here as it is here. Now these distances in my picture don't look the same, but generally that's what should happen. So probably my parabola, if it curved out, maybe a little bit more like that. And I said, okay, this distance and this distance, that looks a little bit better, should be the same, and this distance and this distance should be the same. This should be what my parabola looks like. Now we're not going to sketch any perfect graphs, so don't worry about this part here. But generally you should understand, you should see this, and you should see a horizontal parabola, a parabola that's turned on its side. The focus being inside the curve, the directrix being on the outside of the curve. I should have a vertical line as my directrix if I have this horizontal parabola. But coming up with this stuff here is easy once you recognize that this is what I have and I follow the formulas. Everything we do with conic sections from here on out is all going to be formula based. Once you know what formula you're working with and how to pull the information out of the formula, they really aren't that bad. So here's another one. Focus, directrix, sketch the graph for this particular equation. So we got x squared equals 32y. So that's in the form of x squared equals 4ay. 4a being 32, so a equals 8. So first of all, the x is being squared. So sometimes it's helpful to actually draw the graph before you find the information. So this is what my parabola is going to look like. Here's the y-axis, here's the x-axis. I know I'm at 0, 0 again because of the form. A is 8, which means this distance here is 8 to get me to my focus. This distance here is 8 to get me to my directrix. Okay? So then I have to say, okay, what is the focus? What is the directrix? Well, again, this point. If I'm at 0, 0 and I go 8 units up, that's easy. I can say, okay, my focus is 0, 8. If I'm at 0, 0 and I go 8 units down and I got to figure out what's this directrix, well, this is going to be at -8 and it's a horizontal line, so y equals -8. So there's my focus, there's my directrix, there's my picture. That easy. Okay, here's another version of really the same question, sort of backwards. This question, I give you the information about the parabola and you need to construct the equation. So in this case it says find the equation of the parabola having origin as its vertex. So that means it's either going to be x squared equals 4ax or ay, or y squared equals 4ax. One of these two types. It says the y-axis is the axis of symmetry. Well, if the y-axis is the axis of symmetry, this is the y-axis, that tells me my parabola is going to look like this. If my parabola looks like this, this is the equation I'm going with. Okay? So now it says that -10, -5 is on the graph. So this point right there is on the graph, which tells me that this point is -10, -5, which tells me my parabola actually has to look like this instead. Still, it's a vertical parabola, sort of just flipped over. And you kind of know how that's going to happen. There's going to be a negative involved in here. But so this is my parabola. So how do I use this equation with this point to find the actual equation of the graph? Well, this is an x-coordinate, this is a y-coordinate, right? They have to satisfy this equation. What I really need to know is what a is. Well, if I plug this in for x, plug this in for y, I can solve for a, and I get -10 squared equals 4a times -5. So 100 equals negative 20a. So a equals negative 5. Once I have a, then I go, okay, then my equation is x squared equals negative 20y. That's 4ay. So that's the equation of the parabola in this problem. Now the question says, okay, now find the focus and the directrix. Well, that's easy. We know a. Once we know a, we got a focus. Since it's this kind, the focus is here, and the directrix is here. This being a is negative now. So if I do a this way and a that way, this is going to be negative 5 and negative 5. Focus is always inside the parabola. So my focus is going to be 0, negative 5. And my directrix is going to be y equals 5. Okay, so same problem, just in reverse. We had to come up with the equation. Now here's another one. Find the equation of the parabola having origin as its vertex, the y-axis as its axis of symmetry, and 4, 2 on its graph. Well, again, if the y-axis is the axis of symmetry, it means I'm dealing with x squared equals 4ay. The point being 4, 2 tells me that 4 squared equals 4 times a times 2. So 16 equals 8a. A equals 2. So that tells me my equation is x squared equals 8y. My focus is going to be 0, 2, and my directrix is going to be y equals negative 2. Remember, the form for these things, the form for your focus and directrix, always go back to this equation. Sorry, let me find it. It goes back to this equation here. Where are we? There we go. Where if I have x squared equals 4ay, the focus will always be 0, comma a. The directrix will always be y equals negative a. So if a is 2, focus is 0, 2, and directrix is y equals negative 2. There's not much to these problems because there's really not much to parabolas. If you understand kind of this new method of looking at parabolas in terms of focus and directrix, how we look at the equations of a parabola, one of the variables is squared, how this a part to the equation really helps you find the focus and directrix, you have everything you need.